don't have time to go into this in too much detail. It may be that we'll have to break till, keep some of this till next time. But it turns out that when we measure discrepancy with respect to a datum, there's certain characteristics of that discrepancy measurement that are desirable. And I'll list several of them here. This is non-trivial. I mean, you don't want to just use any discrepancy measurement at all. So first of all, you want something that's dimensionless. By dimensionless, I mean that it's not measured in terms of people or dollars or time. And the reason is, generally you want to arrive at a single number for the discrepancy, for a particular set of parameter values. For a particular point within this space, you want to be able to say the discrepancy, the average discrepancy, say, is X. Okay? And in order to do that, you may have to add up discrepancies across dollars and across people. In order to add those together, they have to be dimensionless. So you won't be adding dollars to people. Yeah, it won't.
So is that for specific parameter model?
Okay. So generally speaking, and some slides will be getting into this, and we'll look at how it's done. You're going to need, so let's step back for a second. Within a stock and flow model, classic system dynamics, deterministic, if you run the model with a particular assumption for beta, particular assumption for mu, particular assumption for tau, and you run the model, you'll get a deterministic result, right? And you can match that deterministic result against historic data using some discrepancy metric, some squared error or what have you. I would argue that even there you want something dimensionless, etc. But you can match it, and there's no use running it again because every time it's going to be exactly the same thing, right? For a stochastic model, you don't have that luxury, and I think I comment on that. I guess it's a later slide yet. You don't have that luxury. So to be clear, within an AnyLogic model, whether it's a discrete event model where you have uncertainty in how long a procedure will take, whether it's an agent-based model, you're going to have some stochastics in the dynamics that are observed for a particular mu, particular beta, and a particular tau. Who gets infected first? Is it the person with a lot of connections or few connections? How quickly does that person recover? All these things are uncertainties. And so what I'm saying is that for a given point in a space, if we were to just run it one time for that point in space, we might get a really good match to historic data, but that might be a fluke, right? It might be a fluke because of the vagaries of chance for that run. And so generally speaking, when it comes to the models we're looking at here, for each point in the space, you're going to have to run the model a number of times. And
you're running it against the parameters of historic data.
Well, you are going to be exploring this space and find the set of parameters who, when you run the model quite a few times with that set of parameters, you find the best match to that historic data collectively. Does that make sense? Yeah. We'll talk about the particulars of the discrepancy, but very, very similar to that. Okay. So it adds texture though, because within Vensim calibration, you'd be wandering over this space trying to find the best value for beta, mu, tau that will give you the best match. And you're just running it one time for each of those. Here you might be running it 10 times for each point in the space and taking the average of the discrepancies for those, something along those lines. Okay, so I would argue that the discrepancy metric should be dimensionless because it needs to be able to combine together discrepancies in dollars with discrepancies in people, discrepancies in incidence rate with discrepancies in prevalence rate. and you want to be able to add together these quantities. It should be weighted, so we might have some data which is of higher quality than other data, better pedigree of data, and we might be able to, might want to weight it more highly. For example, we might have one estimate of the prevalence of an infection in the population that's sampled over, 100,000 people sampled for it, and another that was just a sample of 100 people. And we don't want to treat those as being equal when we try to match them. Analytic, I won't go into here, but concave. I would argue that you don't want to rob Peter to pay Paul here. You don't want to, so to speak, have one thing be matched super well at the cost of all the others. Generally speaking, two small discrepancies of size, say alpha, should be considered more desirable rather than having one discrepancy of size 2 alpha and no discrepancy for the others. You sort of want to sort of avoid having big discrepancies in concentrating those discrepancies all in one thing, and kind of have a lot of small discrepancies perhaps instead. You don't want it to be symmetric, so being off by a factor of 2 should have the same weight. For example, whether we're 2 times the value or 1/2 the value, non-negative. So no discrepancy. A discrepancy in one thing shouldn't cancel out a discrepancy in another. More discrepancy should be worse, not better. And finite input should yield finite discrepancies. There should be not infinite discrepancies. So there's a set of criteria there in terms of discrepancies. And this is